Yeah, way more family.
Good afternoon, everybody. I'd like to welcome all the visitors today to RTI, to our distinguished lecture program of the Fellows Program. I'm Tony Hickey. I'm the chair of the Fellows Distinguished Lecture Series. And this is the fourth year that we're entering. We've had some outstanding speakers, and we have yet another outstanding speaker for you today. I'd just like to ask you, if you would, to turn off your cell phones during this proceeding. For those of you that may need the restroom, it's behind this door outside. You have to go to the right to get to it. And if you are going to ask questions, we're wired today, so there are some microphones that you'll have to come to the microphone stand at the end to actually ask questions. So with that brief introduction, then I'll ask Christina Murata to come up and introduce our speaker for today.
So good afternoon, and allow me to add my welcome to this afternoon's lecture. As Tony mentioned, my name is Christina Murata, and I'm the Senior Director for Air Quality and Exposure here at RTI. And today it is my great pleasure to introduce Dr. Neil Gershenfeld to you. He is the founder and director of the MIT Center for Bits and Atoms, a place dedicated to knocking down the boundaries between the digital and the physical worlds. So I first encountered the genius that is Neil Gershenfeld in the Center for Bits and Atoms when I was a senior executive serving in DHS. This is probably about 5 years ago. We visited the CBA to explore technology for a robot to build a wall. Not a border wall, but rather this is in the aftermath of superstorm flood barrier. So I still regret that some bureaucratic small minds at the Department of Homeland Security and lasting impression on me. It is such a far-ranging portfolio, and it is the most manifestly multidisciplinary place I have ever encountered. Creativity hangs in the air. This is where the future is born. So as I shared recently with Neil, I left the day's discussions just agog at everything I had seen and a deep desire to throw caution to the wind and toss aside my career and beg him to take me on as a postdoc. So my aspirations were quickly shot down by my practical-minded husband. But ever since then, I've continued to follow the work of Dr. Gershenfeld and his team. So for all the science history buffs out there, you know, it's common to think about the advent of certain technologies as fulcrums to catalyze massive global-scale social change, right? So the printing press, the light bulb, nuclear weapons, the internet. It's a very long and storied list. Well, today, Dr. Gershenfeld is going to share with us the latest addition to that list, the transformative power of the third digital revolution, fabrication. Now, it's the subject of his latest book, written in partnership with his equally impressive brothers, and it looks at the ability for anyone to make anything, how we can develop products for a market of one. So, friends, science fiction is fast becoming reality, as you'll see today. The Star Trek replicator, it's coming. The Center for Bits and Atoms is working on it. And what you see with all these tools burgeoning up is that people are able to design local solutions to local problems. Bits will become atoms, and ideas will be made manifest in the physical world at a scale and a price point previously unthinkable. We are becoming creators rather than consumers of technology. So you may be thinking to yourself, well, how does this topic impact my personal and professional passions? The answer is very simply that the third digital revolution will bring wholesale changes to our social and economic fabric. It is going to touch every aspect of our lives, and we should consider how we take advantage of this opportunity. So, understandably hailed as the father of the maker movement, I want to share a little bit about Dr. Gershenfeld's career. He started the Center for Bits and Atoms in 2001 with support from the National Science Foundation. His formal training is in physics, including a PhD in applied physics from Cornell University, and he is a fellow of the American Physical Society, has been named one of Scientific American's top 50 leaders in science and technology, as one of 40 modern-day Leonardos by the Museum of Science and Industry, and as one of Popular Mechanics' 25 makers. He's also been selected by CNN, Time, and Fortune as a principal voice, and by Prospect and Foreign Policy as one of the top 100 public intellectuals. Neil Gershenfeld is a true architect of the future. And thanks to digital fabrication, so is each and every one of us. So please join me in welcoming Dr. Gershenfeld.
Any questions? I think Christina did a great job of what I'm going to talk about. And by the way, you'll be happy to know that Michael was able to route money the bureaucrats didn't know about. So indeed, that was a great introduction to what I'll talk about. In the first TED Talk I did, I had a throwaway line, computer science was the worst thing to happen to computers or to science. CERN had me do a CERN talk on what I meant. And what I mean by that is computer science was fundamentally based on unphysical principles. And I feel like I have the right to say that because CBA was created to look exactly at this boundary of digital and physical. And we did things like the first significant faster than classical quantum computation, programming molecular spin dynamics, cryptography in materials, We were part of creating the first minimal synthetic organism. Among the earliest things called the Internet of Things came out of the research that we did. But more than that, these are some of the people who came through CBA. My student Jason, who worked on the molecular spin programming, built and still runs all of Facebook's computing. And my student Rafi built and used to run all of Twitter's computing. And I'm not a computer scientist and I don't teach computer science, but to do what they do, you can't believe in computer science. Jason has to take billions of dollars and going on hundreds of megawatts and tons of mass and make information. And you can't believe software is separate from hardware. You have to do sort of thermodynamics meets information at this very, very deep fundamental level. So these are some of the examples of the people who have come out of this program. And what's emerging, which sounds obvious but wasn't when we started, is communication was digitized, computation is digitized, all of this is leading up to digital fabrication. And that probably doesn't mean at all what you think it means, and that's what I'm going to spend the next hour talking about. So Claude Shannon wrote what's easily the best master's thesis ever. See, I think I have a picture. So this picture in the upper left corner is Vannevar Bush at MIT made the last great analog computer, the differential analyzer. It's a room full of gears and pulleys, and the longer the computer ran, the worse the answer was. Claude Shannon was a student working on it, and he got so mad at it that in his master's thesis he invented digital. Literally. What he showed in his master's thesis is that switching elements can do universal logic. And then he went on at Bell Labs to create a theory of information. And the heart of that is the meaning of digital, which isn't 1 and 0. What he showed was, I can talk to you as a wave, as I'm doing now, or I can talk to you as a symbol, as we do over the internet. If I give you a symbol, if there's noise above a threshold, you're guaranteed to get it wrong. But if the noise is below a threshold, for a linear increase in the physical resources representing the symbol, there's an exponential reduction in the error to decode it, which means an unreliable device can communicate reliably. So all of technology has very few exponentials, and that's the most important one. So he did that at Bell Labs. An interesting management lesson is some of the old-timers were around when I was at Bell Labs from when Shannon was there, and they explained it took about a decade to fight between analog and digital for the phone system. And the management lesson is the battle was finally won by death, that the analog managers died, and the digital managers took over, and we had a digital network. At the Princeton Institute for Advanced Study, John von Neumann worked with Shannon. He applied information theory to a computer and showed, just like the differential analyzer, if you compute with a symbol rather than a continuous quantity, for a linear increase in the state representing the symbol, the error goes down exponentially, and that meant an unreliable computer could compute reliably. So that's the meaning of digital. It's not 1s and 0s, it's the scaling of detecting and correcting errors. And this exponential scaling means unreliable things can work reliably. So that's the digital revolution. If you trace it forward then, here's the differential analyzer. Thanks to Shannon, that inspired, this is the Whirlwind, which is the first real-time computer. This filled a building at the corner of MIT's campus. It was originally developed for flight simulators, and then it became the basis of the SAGE ground radar system. It was the first significant computer that responded in real time rather than in a batch. And so you can trace modern architecture to this. This was transistorized. This is now at MIT Lincoln Labs. That was the TX. The TX was then commercialized. That became the PDP. This is one of my favorite pictures. This is Ken Thompson and Dennis Ritchie at Bell Labs inventing Unix. And this was the moment. And so the computer in your pocket, most of what it does, you can trace to this here. And this was when computing went from filling a building to something a work group could do. So like Michael funding the project that Christina didn't know about, they could do this without needing management to sign off on that. And so just about everything you do today, video games, email, word processing, happened in this era in computing. So around then, Gordon Moore, in 1963, wrote the most amazing article. And you might have heard of Moore's Law, but if you haven't read the article, go back and read the article. It's brilliant. It's prescient. And he was one of the founders of Intel. And he published the most important graph in history, which is, this is the number of components on early integrated circuits from 1959 to 1962. And he noticed on a linear plot, it looks like not much is happening, but on a log plot, logarithm measures doubling, they line up in a straight line. And so he said, what if that doubling continued for a decade? What would that mean? And so in this amazing article, he really forecasts just about everything that happened ever since in digital technology. Really strongly recommend it. He only got one thing wrong, which was it was 50 years. So around 2015 or so, this is Intel's mainline processors. Around 2015 is when it finally began rolling off. So on the linear plot, it looks like nothing was happening, and then Gordon forecast around 1970 a revolution. The revolution that happened then was the Altair. This was the first hobbyist computer, and it was life-changing, and I'll tell you more about it. Now, if you look at the 50-year run of Moore's Law, on a linear plot, nothing's happening, and then around 2000 or so, it seemed like something big would happen. Our senses are our cognitive senses are linear, but on a log plot, it's just a straight line. And so in 1962, you could see roundabout here, all these points marching along for the next 50 years. So this is Sherry Lassiter. She works for the Center for Bits and Atoms as a program manager, and she was involved in fab labs, which I'll talk about, labs for digital fabrication. She's not very neat, so she has a messy pile of papers. And so many people started to ask for these fab labs that her pile started growing, and she made a joke, and she said, it's doubling every year. It's like Moore's Law. And in writing this book, I plotted the data. And so this is fab labs. I'll tell you much more about them versus years. And they've been doubling for a decade. Doubling time is a year and a half. We have more data than Gordon Moore had. And so what this book and what we're here today to talk about is, what if this continues for 50 years? What does 50 years of doubling of digital fabrication look like? So here's the beginning. This is data point number one. MIT invented computer-controlled manufacturing in 1952. Jet aircraft were emerging. There were parts too hard to make by hand for the machinist to turn the cranks. And so the early real-time computers were connected to an early milling machine to automate manufacturing. So that's the birth of computer-controlled machining. There was just one of these at that point. If you fast forward now to the most state-of-the-art 3D printer, nothing's changed. There's a computer. It's controlling an end effector, and the end effector either deposits or removes material. The information isn't in the material, it's in the controlling computer. The end effectors have changed, but it's still the same architecture. So I'm going to start with number one. This is Earth, so we're here. This is the whirlwind. This is NC Mill, 1952. This proposal for CBA pretty literally was, I wanted one of every machine to make anything. And that's what, or actually you funded, thanks to your tax dollars. That's what we put together. This facility was one of every kind of tool to make anything. But I had a problem, which is it would take a lifetime of classes to learn to use all those tools. So I started a class modestly called How to Make Almost Anything, to use those tools, and a series of surprises followed. The first was, it was aimed at 10 or so research students, and every year hundreds of students try to get into it. The second thing is they didn't want to take the class primarily for research. They wanted to make stuff, which in retrospect isn't surprising. But then what was surprising is what they did with it. So Kelly was the star the first year, and she was a sculptor, no technical background. This was her semester project after learning these skills. Of a young child, they go crazy left home alone. This is an alarm clock you wrestle with to prove you're awake. This was a dress instrumented with sensors and spines, and so if somebody gets too close, it defends your personal space. This happened so consistently year after year, I realized the students were answering a question I didn't ask, which is, what is digital fabrication good for? I was asking how to do it, but not why to do it. And they were showing this. This is Ken Olsen, who led the commercialization of the TX, which became the PDP, which became DEC. DEC spawned on Route 128 in Boston, Wang, Prime, Data General, the whole computer industry. They all failed when PCs came, and Ken famously said there's no reason for a computer in the home. Little context, but that's what he said. The mini computer industry saw personal computing as a toy, and it killed them. And what the students were showing in that class is the killer app of digital fabrication is personal fabrication. It's not mass manufacturing of what you can buy in stores. It's personal manufacturing of what you can't buy in stores. So that led up to this. This is Boston. Here's the PDP. And for outreach for the NSF, around this point in time, Congress passed what's called GIPRA, which is agencies had to measure social impact. NSF didn't know how to do it, so it turned to big programs like ours and said, you measure social impact. We didn't know how to do it, but we thought the machines are cool. So we had this idea, inspired by the analogy with the PDP, what if we set up local versions of the research tools on campus and just let people get access to them. So that started this Fab Lab project. This is an amusing one. This is Frosty. This is Vestmannaeyjar, Iceland. If you remember the pictures of a town disappearing under lava in Iceland, that's here. Little tiny island off the coast of Iceland. This is a Fab Lab. Think of it as the mini computer. It's about a $100,000 investment, about 2 tons. One of the most interesting machines back there, so Ted and Sally are over there. Ted? So that's Ted and Sally, and they make these about 20 minutes away, depending on traffic. On the other side of Durham is ShopBot, and they make this large format tool that lets you make furniture, boats, bicycles, composites. People have made whole houses on this machine. So large format tool. There is a 3D printer, but the 3D printer is actually one of the least useful tools. There's precision machining, vinyl cutting, additive, subtractive, molding, casting, composite, surface mount rework. It's about 10 processes, only one of which is 3D printing. They're all computer controlled. But for many purposes, the 3D printer is the least useful one. All of these are ways to transform material with a computer. So, and you see they're all in a common shared space. They're not segregated. And so with those, you can do all of this. Skateboards, kayak, bicycle. This was a whole house made that way. Antennas for, this is in Afghanistan in Jalalabad, antennas for civic networks, thin client computers, medical sensors, consumer electronics, production tooling. All of these are made not in factories, but in one of these fab labs. So this was the surprise. We opened one in inner city Boston, and then we thought we'd go back to the lab and work. But there was a strong Ghanaian connection that led to doing one in Sekandi Takoradi on the coast of Ghana. Then there was a strong South African connection. We did a first one in Pretoria, then Soshangovi. And then they started spreading. And so the lasses, we call Sherry Lassiter Lass. And so rather than Moore's Law, we've started calling this Lass's Law. And the Lass's Law is these are doubling every year and a half. We didn't plan that, but every year more and more sites want to join this network of Fab Labs. And so this is about as far north as you can go in Norway, as far south as you can go in South Africa. Actually, one of the ones we're doing here is off the bottom of the page, the furthest tip of South America. This is one of the most remote parts of rural India. This is in Bhutan. All over the world, you can't make this up in Cambridge, Massachusetts. All these places pulled these labs. And so this is what some of them look like. This is one in Detroit. There's a lot of press around bankruptcy and problems in Detroit. This is working with at-risk youth, kids in juvenile justice, and transforming the community. Some of what they do is commercial activity. Some of what they do is sort of a post-money economy. Rather than getting a job to get money to buy something, you can just create the thing. So they do urban agriculture, they create civic infrastructure. Some of what they do isn't for money, it's for expression, it's for design, it's for community. This is an amazing lab I mentioned in Bhutan. He's the prime minister of Bhutan. There's a fabulous TED talk I really strongly recommend. Bhutan is based not on a gross domestic product, but gross national happiness. And it doesn't mean they're happy, but it means they measure the output of the economy in the well-being of the people in the country. But it has real teeth. The equivalent of the IRS is the Gross National Happiness Office that assesses well-being. But they buy crap trucked in from India. They can't make anything. And so we're working with them to make gross national happiness physical. This is in Holon, a mixed community in Israel. This is an amazing group of labs at the Protestant Catholic boundary in Northern Ireland, Belfast and Derry, right at what are called the peace walls that are really the war walls. This is an arts colony in Maine. This is a really interesting one with Alaska Natives. Great cultural traditions, terrible suicide, unemployment, alcoholism, and the kids sit around playing video games. And so this is mixing traditional crafts and materials with modern digital fabrication. These are what these places look like. All with that, like the growth of the internet, they all share what was in that picture I showed you, the same set of capabilities. So people and projects are shared in this network. And so it spawned projects like, this is a really interesting one doing aquaponics for urban agriculture. So you can grow food much more efficiently than digging in the dirt by precisely providing nutrients and lighting. And so this is using the labs to make aquaponic systems. Rather than buying drones, this is making drones, but then making businesses that don't sell drones, but sell data from drones. This is customizing furniture. This is citizen science, environmental monitoring. All of these are programs that grew out of innovation in these labs locally, becoming large-scale programs. To keep up with that, we had to spin off a nonprofit foundation because traditional aid groups don't do speculative technical risk. We had to create a community portal for fabrication. We had to create a Fab Academy, which is not central learning, you come to MIT. It's not online learning where you look at a computer screen, which is sort of like BitNet. This is like internet. Students have peers in work groups with mentors locally learning digital fabrication, but then we connect them with broadband video and content sharing in a global network for global classes. So it's a global classroom of local learning sites, and it's teaching digital fabrication, the same things I teach at MIT, but now in these sites all over the world, and everywhere we open them in their most remote locations, the same bright, inventive people appear. That inspired George Church to overlay on this network a bio academy where roughly you use a fab lab to make a bio lab and then you teach biotechnology. There's a new program using the network to do Fabricademy, which is textile technologies. All of these are using this network to do not distance education, but distributed education. Then it has really interesting political implications. This is the mayor of Barcelona. Barcelona has over 50% youth unemployment. It's an amazing number. A whole generation can't work the way we understand it, but they've got this fabulous design sense. And so he's starting a countdown to urban self-sufficiency. Today, they consider Barcelona Pito, products in, trash out. Products come in one side and trash goes out the other side. They want to be Dito, data in, data out. They want the bits to come and go, but the atoms to stay. It's not protectionism. It's not traditional agrarian economy. You need to be globally connected for knowledge, but then have the means to fabricate locally. So they're spreading digital fabrication as part of urban infrastructure. This was a lab we ran at the White House, and Bill Foster, the remaining physicist in Congress, has recently reintroduced a really interesting piece of legislation.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress.
It's now 100%.
But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or for part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives which supports the goals and mission of the National Fab Lab Network as in the best interest of our people and the best interest of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have the chance to visit Neil and see the progenitor.
So in the House, the co-sponsors were Bill, who's the bluest of blue representatives, and Thomas Massey, who's the reddest of red representatives. But on this issue, they're absolutely, completely coincident. In the Senate, it's Chris Van Hollen and Lisa Murkowski. And it's a really interesting piece of legislation. It charters rather than funds, because the money is sensitive, but there's a lot of sources for it. It charters as being in the national interest, universal access to digital fabrication in the same way that we have universal access to communication and computation. But isolated labs fail. The strength comes from being in networks. And so it creates this infrastructure to create a national network of connected local labs with an initial goal of one in every congressional district. And so if you like this talk, this is a really great way to immediately follow up. This is what Barcelona is now doing. From making labs, they're now taking a whole district, Poblenou, and they're remaking it as a prototype, not just smart city, but fab city, as a sustainable district, producing much of what it consumes sustainably on the district level. Once a year, all these labs meet. This is coming up in France in July if you're really interested and want to meet the global network. So to keep scaling, this is now Davis Square, the community I live in. 1,000 is an interesting number. 1,000 is the number of major cities on Earth. That's where we are now with Fab Labs. And that's roughly the number of mini computers. What came after the PDP was the Altair. And this was life-changing for people like me. With the Altair, when it first came out, the killer app was you could flip switches to load a binary program, and then you ran it, and the lights would blink. So on that, a company was started, Micro-Soft. They eventually took out the hyphen. And the first time this came to the Bay Area, it led to a meeting which became the Homebrew Computer Club, with a whole generation of computing pioneers got their start on this, not because it was useful, but because it was personal. And that got up to millions, which is not yet the number of people, but it's the number of towns. And so for that, we're transitioning. So today, to get a Fab Lab, you buy the machines. These are all rapid prototyping machines made on the rapid prototyping machines. And so, in fact, this was an amusing one. This fits as TSA carry-on luggage, and it's a little fab tool in a briefcase with a kinematic mount and interchangeable heads, and it can print or cut or mill. And so it's a whole fab tool in a box. And not just that, but it's made on the fab tools. And so we thought that this is great, we're done now. These are fab tools you can make in fab labs. And so to get from 1,000 to 1,000,000, you don't buy one, you go to a fab lab and you make a fab lab. It didn't work though, because this was too hard to do and too few people could do it. So this led to a bunch of companies like Form Labs, or in fact, this was an interesting one. One of those machines sat on Ted's desk for a while at ShopBot, and it led to spinning off this interesting company, HandyBot, which makes little version of the big machines ShopBot sells. But Ted did something really interesting. Rather than putting it in the existing factory, he made a new factory, which was about the size of the stage, as basically a little storefront factory to show that you can do manufacturing on very local scales. And so HandyBot is sort of inspired by, it's a descendant of those machines, and they have a whole little bestiary of these little community scale machines. So these are all a next generation of fab tools that are faster, better, cheaper, aimed at individuals, not industry. But we still wanted to go beyond that. And so to make stuff today, you do CAD to design it, then you do CAM to turn it into instructions for a machine. Then you send it to a machine controller to interpret it. Then you send it to a motion controller that finally does something. And so it's like a bad party game. And so we've had to merge CAD, CAM, machine control, and motion control end to end into what you can think of as object-oriented hardware. So software used to be like Fortran, just a big program, and you had to write a new program for something else. You now make software out of objects. We're now making machines out of objects where the software mirrors the hardware. So, this is a newer generation. So here's Nadia again. This is James, who now, he runs technology for Zaner, which makes things like the Frank Gehry buildings. And we had a visitor from NASA who wanted airfoils. And so each of these are machine parts, but each part is a physical part, but it's also a network node, and it's also a node in a program. And so you connect the physical degrees of freedom, and then you connect the network nodes, and then you connect the software nodes. And so what it lets you do is rapidly compose machines. It lets you do rapid prototyping of rapid prototyping machines. And so you could make a new machine for every project just by assembling the hardware modules with the software modules. That inspired this. This is Jens, an amazing designer from Norway, who spent 2 years touring fab labs. He was so excited by them. This is a neat moment. This is Obama's grandmother in Kisumu in Western Kenya. And he was in Japan, and a fab lab in Japan designed Obama slippers that then made in a fab lab in Western Kenya, and then he's presenting it to Obama's grandmother. The previous image I showed you, the modules involved technical parts sourced by Shenzhen. These are now modules, but these are modules made on the machine you're looking at. So these are modular machine building components, but now the modular machine building components are made on the machine, made out of them, so you can make more of them. And this is a rapid prototyping class where we now took the students through in a week. They made a machine, and so this one, rather than printing or cutting, this is to plot out custom pancakes with grayscale displays in the images on the pancakes. But it's not just rapid prototyping, it's rapid automation, but this is a group of machine beginners who in a week designed and built a machine, transitioning to this idea that you don't go to a fab lab to make something, you go to a fab lab to make the next fab lab. And this is here today. That's not a forecast. The technology, most of the technology can be made in a fab lab today. So to keep scaling, this is the neighborhood I live with in Davis Square. 1 billion is the order of the number of people on the planet. And 1 billion is when we got to the stage of things like smartphones, when the number of them is within a prefactor of the number of people on Earth. And there we have a problem, which is this is the inventory in a fab lab. You can make almost anything, but it rests on this inventory. And if we zoom in, this is part of what we get from the electronics vendor DigiKey. And you need all of this in the supply chain for the fab lab to work. And so if we zoom in on that, DigiKey sells 500,000 capacitors, 500,000 resistors. That's not the inventory, that's the number of distinct SKUs, every one of which has its whole inventory. But what's crazy about that is conceptually it's only 3 properties: conducting, insulating, and resistive. And so what we've started doing is building what we call digital materials. So take a state-of-the-art 3D printer and compare it to a child with Lego. Because the geometry comes from the Lego, the child can make something bigger than themselves, unlike the 3D printer that has a build volume. Because you can detect and correct errors, the Lego tower is more accurate than the child. When you 3D print, if something goes wrong, errors accumulate in it. You can join Lego bricks made out of unrelated materials. It's hard to 3D print dissimilar materials. And when you're done, Lego doesn't make trash. You disassemble it and use it again. It's hard to reuse output from 3D printing. That idea isn't new. It's a few billion years old. That's how life works with amino acids, which I'll talk more about. This is what Shannon and Van Neumann taught us. Trash is an analog concept. Trash means there isn't enough information in the materials to know what to do with it. Digitizing not just the design but the materials mean discrete sets of parts with discrete set of relative orientation and position, so you can detect and correct errors in their construction, just as we learned from Shannon and Van Neumann. And so in this project, here's a design tool to design, in this case, electronics. So these are electronic components, but they're made out of these fundamental properties like conducting and insulating. You can model the physics and then export codes to assemblers. And then here's a first generation assembler that this looks like a printer or a milling machine, but it doesn't print or cut, it adds and removes. And so it works relative and locally. It assembles to the structure it's building, and it snaps together these parts. And this was a first generation one to build electronics by assembling and disassembling. And when we started studying how to assemble structures, some surprising things happened. Today, to make a jumbo jet, you need a tool the size of the jumbo jet to lay up the carbon fiber parts. You need a tool the size of the jumbo jet to cook them. You need a jumbo jet bigger than the jumbo jet to carry them. For both Boeing and Airbus, it was $30 billion investments that almost killed them. We showed if you make little loops of carbon fiber and you link them reversibly, by an order of magnitude, we set the record for the highest modulus ultralight material. And then you can do this. You can make assemblers that walk on the structure as part of the structure to locomote, and then they can pass parts to build the structure. And so we're developing, and this is, again, the work that Christina mentioned at the beginning, robots to crawl on these structures to build the structure, where the robot is part of the structure it's building. And then once you do that, you can do things like this was a project. There's been a long-standing goal to make airplanes that can flap their wings, that can change shape. But they were heavy. It was hard to make the mechanism. Doing it this way, by mixing these types of parts that are rigid and flexural, you can design airplanes that can change shape, which is much more efficient and much more agile. That was the first generation. The biggest one now is about the size of this stage. And so to get up to 1 billion fab labs, what you need to do is, you can make all of this today, but you need all of the vendors. And so to get to 1 billion fab labs, we want to eliminate all of the inputs and reduce it down to the small set of materials. This is now my home office, and it's full of smart devices. And this is a Nest thermostat. The Internet of Things is approaching 1 trillion. It's not quite there, but we're getting up to 1 trillion devices on the Internet. The Internet address space broke around 1 billion, and we're heading towards 1 trillion. If you look at this stack here, the Nest thermostat pretty much does exactly what the PDP does. It's the functionality of the PDP, but it's now in this box on the wall. And so as we start coming up in number and down in cost, then there's a problem, which is if you wanted to place the micro parts I showed you, and you wanted to build a meter volume out of millimeter parts, it means you need to place 1 billion parts. At the speed of inkjet printing, that would take a day, which is about the speed of 3D printing. So that's fine. But if you wanted to go 10 to the 6, so from microns to meters, that means you need to place 10 to the 18 parts, and that would take 3 million years, which is a long time for output. The body's solution is a really interesting one. Ribosomes do exactly what I'm describing. They're slow. A ribosome puts 1 amino acid a second, but ribosomes make ribosomes. And so a cell can have 1 million, and you can have 1 trillion cell. So as you're sitting there right now, your body is placing on the order of 10 to the 18 parts a second. And so the solution is not parallel fabrication, it's massively parallel serial fabrication. So this is the real inspiration for this project. This is your inventory. You're made out of 20 parts. These are the amino acids. And what's interesting about amino acids is they're not interesting. They're hydrophobic or hydrophilic, basic, acidic. They have these very simple properties, not unusually so, but this is the motor that's moving me right now. This is how I'm smelling. This is how I'm thinking. These parts can be assembled to make these things. The motor isn't done by designing a special motor material. You take these 20 basic properties and you compose them. And so you can design those. This was the project I mentioned we were part of to design an organism from scratch, and you print it, which is about 6 months of work to make the genome and boot up a cell designed in a computer. But there you're limited to the biological materials. So the fundamental project we're doing underlying all of this is based on this analogy. Your genome codes for a primary sequence of these amino acids. They then fold into geometrical motifs, spirals, helices, sheets. Those make structures that are functional, that can do things like donate or accept electrons. And then those make molecular machines, like the motors and the synapses. So I was at ARO, the Army Research Office, this morning, where we're doing a project to try to reduce the whole DoD supply chain to 20 parts. And it's based literally on doing primary, secondary, tertiary, quaternary structure, but now with engineering materials. And so this is a rigid part, this is a flexural part that lets you make a mechanism, this is an electrical part that lets you make logic, this is a magnetic part that lets you make actuation, this is the equivalent of a synapse part, and then when you start assembling them, all of this is about the size of a penny, with just a few parts. A rigid and a flexural part lets you make a mechanism, an actuator part lets you drive it, and then you can make motors. And these are just beginning parts of designing an assembler that can assemble itself out of the parts that it's assembling. Then you have to do something interesting. To do that, you have to design a structure that communicates a computation for its construction. So this is a merge design tool where you simultaneously place, each of these blocks is one of the parts I showed you, you place blocks of functional materials that compute, communicate, and construct to design the self-assembler. And that actually led to an interesting collaboration. Having done that, we started working with a very interesting video game company on turning the design tool into an immersive video game. So this looks better, but these are the same parts I showed you. This is just visual representations of them. This is an immersive VR environment you walk around in with these blocks, and then with them you design functional electromechanical system. And then from there, you can do things like design creatures and robots. And so if you're familiar with Minecraft, this is like Minecraft, but it's Minecraft with real physics. And so this is both a fun representation, but it's actually a serious design tool we're using to design the self-assembler. And so you can then, in this world, run around and do things. But again, this is doing it with real physics in the design of how these work. So interestingly, stepping back to where I started with computer science as the worst thing that happened to computers or to science, the reason I say that at heart is I worked not directly, but once removed with von Neumann and Turing. I worked with one of each of their students and learned about what they were thinking. Modern computer architecture is credited to von Neumann. He never wrote about it. The only thing he wrote was an army report on how to program this thing, the EDVAC. And it was a hack. It was a hack to make this work. And ever since, the computer in your pocket, the computer you probably sit in front of all day, is saddled with hacks to make this thing work that have long outlived their usefulness. Here's where Turing introduced Turing machines. It was never meant to be a computer architecture. It was for a fundamental mathematical proof. Both of them ended their life looking at how computation relates to fabrication. So von Neumann ended his life by inventing cellular automata to study a machine that can communicate a computation for its instruction. And Turing ended his life studying morphogenesis of how genes run programs to create form. Those were theoretical studies, but we're at a point now where we can do it for real. So we can actually design morphogenesis. And what I showed you in this roadmap to the replicator is how to build von Neumann's automata. The Star Trek replicator, the fundamental insight is it's all about embodying computation in materials. It's not a zoo of fancy materials going in. It's a way to compose simple materials hierarchically to get complex function. But to do it, you have to completely merge communication, computation, and fabrication. So fabrication is the third digital revolution. Isn't unrelated to the other two. It completes the other two. It merges communication, computation, and fabrication. One more way to understand this is a fun event we did with 20th Century Fox for bonus material, the movie The Martian. They wanted to show how do you actually bootstrap a civilization on Mars. And the term of art is ISRU, in situ resource utilization. And the model for it is furnace to make hand tools, and at the end of book 7 you have a machine shop, and it's roughly how to repeat the Industrial Revolution. And the assumption has been you have to do the Industrial Revolution on Mars to make a civilization. You should now recognize the images behind me. What's emerging is not that. You have to essentially create life in non-living materials. You have to source these 20 or so material properties, assemble them in these building blocks, and then hierarchically compose them to create all of technology out of 20 or so parts. You're really getting at this fundamental question of what are the minimum building blocks to bootstrap a viable civilization. So digital fabrication, you can think of it as the 1952 NC mill. We're now in this picture of going up in number and down in cost exactly at this transition. There was one of these, there was 1,000 fab labs. The fab lab lets you really make almost anything, but you need lots of vendors. We're just now transitioning to fab labs making fab labs. And so here, digital fabric, so the fab lab is digital if you view the whole thing as a machine. If you don't look in the room, data goes into the room and functional things come out. Things go in the room and data comes out, but inside in the room it's 10 or so machines. Here, the machines are making the machines, and so you can do, instead of 10 different machines, one machine that can do 10 different things. But you still need DigiKey, you still need all of the vendors. Here, we're reducing the inputs, we're turning the parts from 500,000 resistors to 3 material properties. But eventually that can't place the parts fast enough. And then here you fundamentally need the assembler to assemble itself to scale capacity. And each of these things is happening at the same time. They're all here today. But this ranges from right now to, say, 50 years in the future to finish on different length scales. But we're right at this point. And this is the moment when the internet emerged, the analogy. And so we've been spending so much time with things like heads of state and military generals and aid groups because jobs, economy, import, trade, all of these sensitive issues all have been based on a false dichotomy. So if you take globalism versus localism, it assumes they're in opposition, and it assumes you go to school to learn, then you get a job to work, and then you get money, and then you get a thing. But if anybody can make almost anything anywhere, it cuts right across that and fundamentally challenges what is work, what is money, what is education, how does the economy work. I thought the technology was hard. That's actually been humming along. What's been really hard is we've had to invent a whole new set of organizations to sort of turn on its side what is education, what is aid, what is industry for this world where anybody can make anything. And so that might sound like an ambitious projection, but remember we have more data than Gordon Moore had. You can really see technically what the next 50 years is going to look like. But to live in that world, it really requires revisiting the assumptions of how we live, learn, work, and play today. And so the real grand experiment is if anybody can make almost anything anywhere, how will we live, learn, work, and play? And so that's what I invite you to join in to help us answer. Thank you. Questions?
Yeah. If you have a question, please come use the microphones on either side of the aisle.
Thank you for a fascinating talk. I'm wondering about the manufacturing of space and time. I read something interesting about lengths of qubits that bridge time. So I'll pass that out. On the other end of the scale, I'm wondering, I noticed that there were some empty areas on the land mass, like in Russia and a few other places, and I'm wondering about the political resistance, and people are going to wonder, how do I monetize that, rather than why should I monetize it?
Yeah, so what's interesting about monetizing is these are actually, there's not a lot of fab labs in the east of Russia, but there's not a lot of anything in the east of Russia. The map isn't, there's some exceptions, but you know, at low resolution, it's not that far off from where the people are. What's interesting is we actually have great collaborations both on the ground, but also with leadership in places like Russia or China or Pakistan, where the people who should be threatened by this aren't. They either see it as a toy or see it as empowering. This is a surprising issue that doesn't really run into a lot of opposition. It's very disruptive for traditional notions of governance, but even authoritarian regimes see this as empowering and as a great thing to do. This is really an unusual issue that crosses all of those traditional boundaries. And again, where these are is nobody picked this, just each of these is somebody opened one and it led to the next one. That got us up to the stage of 1,000, but the next, again, this is like when the internet began to leave the research lab. And so we're just now at the next stage is how does this keep spreading around the world?
You address governance as well?
You said governance? Yeah, well, so governance is a complex question in that there's a couple senses of governance. So there's traditional governance. So let's see. in Bhutan, the most fundamental appliance in a house is the rice cooker. The sort of the heart of the house is the rice cooker. They all come from Japan. So a factory in Japan has to make them. Then it has to get carried to a port in Japan to go on a ship to get to Bhutan. Then it has to get trucked imported into probably India. Then it has to go down a road. It has to cross a border. It has to get into Bhutan. Each of the steps somebody pays somebody. Eventually you get the rice cooker. If you make the rice cooker in the Fab Lab in Bhutan, which is not a hard project, all of those stages go away. And so on one side, a lot of what government does, you don't need anymore. On the other hand, when Christina was at DHS, we did an event on this, and it was this really interesting split of half of the room said, my God, we have to control this. The other half of the room was horrified at the first half of the room, saying, not only do we not need to control it, and not only can we not control it, we need to help this propagate because it's getting at the root issues that we're here to address. But it's not based on hard power, it's based on soft power. If you make the rice cooker, you could make a dangerous rice cooker, but there isn't a central authority that can authorize rice cookers. What you need to do is create incentives to share rice cooker designs. And this is really serious when you get to things like a Fab Lab can make a bio lab, and then you can do biotechnology, and then you could make bioweapons of mass destruction. That's not controllable. It's just not controllable. But we've been working with groups like DHS and FBI on how to provide incentives for people to work in the open. And so all over the world, we have people who come into the labs with creepy ideas, but they also become part of communities, and the communities help shape them. And you can't prevent people with creepy ideas, and you can't control the technology, but what you can do is provide incentives to do it in community settings, which is a really powerful tool. Is he
yes,
back there?
Yes, thank you for your presentation. It has been really warming. So with all the technology and with your fab labs, what happens with the data? Who owns the data? And all of the morality issues that we have that surrounding technology today.
Yep. So if you go back to the scaling, round about here was when Amazon, Google, Facebook emerged, and then with the I know the founders well, with reasonably best of intentions, they backed into this now kind of nightmare scenario of fake news and all of that. So what does that look like here? Something interesting that's been happening is there have been multiple attempts to create the Facebook or Google or Amazon of digital fabrication. So far, none of them have gotten traction. And it may be that this is a different model. So last night, I had dinner with RTI at Nana's in Durham. And if you think about Nana's restaurant in Durham, we didn't go to a chain restaurant. That wouldn't be a good dinner. They went to a good local restaurant. And I had an interesting tuna dish at Nana's. And Nana's didn't get the recipe from an online repository. It was based on, their experience with cooking and, years of cooking. Cooking in restaurants haven't gone the way of Google and Facebook because it's physical and it's personal and it's local. And it may be this is because you're going from bits to atoms, there isn't the gravitational force that centralizes it, but you end up with a much more distributed solution to it. And so the whole Fab Lab network is an exercise in soft power, in lateral alignment. And the attempts to make a central control point so far haven't been working. Also, one interesting thing is, let's see, A fun thing you can do in a fab lab is make high-gain antennas and radios to make regional networks. When we started doing that in South Africa, it violated the law. And counterparts in the government asked us to do it to violate the law, to help make the point that the law made no sense. So sort of watch this space as it plays out, but so far it's evolving in a different path from the gravitational forces that pulled everything together in the Google era. One other note that's related to your question is intellectual property. And there it's a really easy answer, which is, when I design a robot for Airbus to make jumbo jets, I file patents because there's a significant barrier to infringement and you can identify infringement. Nothing you do in a fab lab is protectable because there's no barrier to infringement and you can't identify infringement. But that's not new. That's exactly what happened to software. Not all, but most software has evolved to open source. Even amazingly, Microsoft has a complete open source subsystem built into Windows now because they couldn't compete with it. And it's the same story here. You can make money from things and benefit from things by openly sharing the design, but you make the money from what you do with it and how you use it. And so this is very much the transition to open source, which doesn't mean it is an economy, but it's not based on protecting secrets, but now it's made physical.
Thank you.
Yep. Let's see. I see you, but go back to, I think they want you to use the microphone, you two, and there's somebody back there. So come to the microphone. Yep.
Thank you for a thoughtful presentation. There's a lot going on there. Have you given some thought as to what happens in a consumer society where individuals have the capacity to just make whatever they want to at very low cost? What does life look like, in your view, in 20, 30 years out?
So first of all, my view doesn't matter. The reason I say that is a little bit of what I do is the high-level story. Most of what I do is the plumbing. The day job I'm working on is internals of CAD, CAM, machine control, motion control, the plumbing that makes it work. That's my core competence. The rest of this isn't my story. It's the world's story. And, Ted and Sally have been to a number of these gatherings, and they're amazing because, like, this annual FAB meeting is the most diverse gathering I know. It's rich, poor, north, south, male, female, white, black, so any axis you can think of, but it's all the same person, just in all these different packages. There's a crazy statistic. Businesses spun off from MIT are the world's 10th economy. It falls between the economic output of India and Russia. And that's a crazy number because it's only a few thousand people at a time. It's not that they're clever, it's that they're in an environment that lets them sort of act on being clever. And what we find when we open these fab labs, in every one of these places is like, we opened it and Ugyen appeared, and he's absolutely as clever, bright as any of the students at MIT. There was just no place for him. He's now doing the Fab Academy in rural India. The world is full of this untapped brain power, and these labs act as magnets for them. So to come to what it looks like, Blair has an interesting model at his lab in Detroit, that people in the lab spend about a third of their time on commercial activity that makes money for the traditional economy. The making money, though, a lot of it isn't what you think. Remember, the big lesson from the dot-com era was Google doesn't sell search, it gives away search, and it sells the consequences of searching. The analogy here is one of the core things in Blair's financial model is he takes at-risk youth, he delivers better life outcomes than existing social services, quantifies that, measures it, and delivers the economic impact of the transformation of kids in the community. And in that sense, many of the Fab Lab business models, this one is selling integration of Protestant and Catholic communities as a real measurable outcome. Many of the business models don't sell the thing you make, they sell the benefits of having made something. It's a really important distinction. But to go ahead, in Blair's lab, about a third of the time is making money for the traditional economy. About a third of the time is making things for the community, but not for money, for yourself or for barter or for infrastructure, of turning consumers into creators. It's not utopia, but it's sort of a post-money economy. And a third of the time is not for economic reasons. It's art, it's play, it's education, it's using the tool. This whole assumption that we work and then live to consume, and we consume by picking things from a screen, is a relatively recent invention, and it's not fundamental. And in each of these places, what's emerging is a post-money economy where your livelihood isn't based on numbers in a bank account, it's based on the means to create to meet needs. And so this picture I showed in Barcelona is aimed at the next step in that. So there was one Fab Lab in Barcelona, then they put one in every district. And I was at a wild event right at the edge of Barcelona, up by the hills. There's a very poor area where like immigrants get pushed. And one of the new labs was going to go in there, and they occupied the building and had a protest to say, we don't want machines, we want a food bank. We don't have enough to eat. And I was at a really interesting event. Barcelona that can help you grow food, to do urban agriculture, and make toys for your children, and start businesses. And there was this amazing moment where they said, oh, actually, I want that. And so Barcelona is now doing this experiment to take a whole district of the city and start to link sources and sinks and recycling and production. It's not going to be a step function. Every year in this 40-year countdown, they're working to make more and more of what they consume sustainably locally. And so I think this is a really good vignette of what this model looks like, for what the future will look like. But in this, you don't first go to school to learn, then get a job to work, then go to a store to buy. All of those things are merged as a lifelong activity.
So it's a great presentation. I'm curious, so you're borrowing from biology with this new fabrication. Is there any possibility that you're going to see critical points in manufacturing, areas that might fail, where you would feed back to the biology in terms of disease? Because it seems to me you're going to understand so much more with the amount of work that you're doing, that structuring, you talked about secondary, tertiary structure and so on, you might learn something about where things fail.
So there's an interesting kind of recursion. So first of all, the way I would describe this is we're not reverse engineering biology, we're forward engineering biology. We're just trying to learn from how digital meets physical to digitize fabrication. And every step of the way, we discover that we're rediscovering what biology already did. So this deep biological parallel wasn't how the project started. It emerged as we were going, and we looked over, and we saw this really interesting alignment. So in molecular biology, nothing I said in the last hour is new. Molecular biology does every single thing I described, and it's been doing it for 4 billion years. So one part of what we do is that one of the most interesting projects in the lab, we're part of a collaboration, is not just to design a genome, but actually design a whole cell from scratch, to actually refactor the building blocks in a cell. And we're doing that to make cell-like things that can do what cells can't do. So all of that is directly using these ideas in biology, but it's just a little bit off of where traditional biology is, because molecular biology does everything that I'm describing. Where that boundary, I think the richest place for that boundary is, we're part of an interesting new design project with DARPA on when we can place not just 10 to the 9, but 10 to the 18 parts the whole notion of how design works breaks. Evolution is widely misunderstood. Evolution isn't random search. Morphogenesis in biology, my body doesn't anywhere have 5 fingers. It stores a program that when you execute it results in 5 fingers. And then evolution searches in a very careful way over programs. It doesn't search over body plans, it searches over programs to make body plans. It's sort of code that writes code. And a really interesting point we're doing right now is how to introduce morphogenesis into engineering design to design, to write programs that make things. And so there's a rich interplay between these ideas in biology. But I'm fairly humble on what we'll teach biology because biology knows all of this already.
Yeah. No, I think that we often don't look in the right places. The biology knows what it's doing, but you may point in directions that we don't look.
Yeah, yeah. Okay.
Hi, great lecture. I have a 2-part question. Could you comment on the limits surrounding the materials that could be used in fab labs? Think of density, volatility, etc. The second question is, could you also comment on these methods and techniques in terms of solving today's challenges? Recycling as an example.
Yeah.
We have a lot of plastic waste.
Yep, there's short and long-term answers. In the short term, if you go back to this unreadable list of the inventory in a fab lab, we do a lot of work. There's a small set of high-tech consumables and a lot of low-tech, locally sourced consumables, all designed to minimize the environmental footprint. So for example, we don't etch circuit boards. We do precision machining that just makes a little bit of dust as waste. Or we don't use carbon fiber epoxy, we use natural resin, natural fiber to do TEDS machines to make tooling to lay up composites. Or instead of petrochemicals, we do molding and casting with essentially fancy concrete with mineral-based materials. And so in the short term, we do a lot of work on friendly materials in the supply chain. And there's some interesting work on things like how to grind plastic waste up to make filaments that you can then re-extrude. So the machines that make machines for recycling machines in the short term. But there's a lot of good work on that, but my real focus is to make trash just completely go away, because there is no trash in a forest. And there's no trash in the Lego playroom, both for the same reason, which is it's decomposable. And so the real focus of the research behind all of this we're doing is how to assemble materials so that you can disassemble them and reuse them. And the really surprising part of that is you might think, you know, if you look around the room, the podium and the microphone and the bottle, you need lots and lots and lots of different materials. But what we're finding is it's only a fairly small set of material properties that when the parts get small enough can assemble them to get the range of modern material properties. And so the research is really aiming at putting information in materials. Trash and recycling are only symptoms of analog materials. And we're trying to digitize the materials. Yep. Over here, I guess you were next. Go ahead.
Well, he was up before.
Okay.
Okay. I think you partly answered my question there, but everything is chemicals, as you just described, and I don't understand the difference, and maybe you can explain it to me a little bit, the difference in what you've tried, which is tremendous, like almost an industrial revolution, between 3D and 4D printing and what you're doing.
Oh, it's very easy to explain the difference between 3D. So, 4D printing was developed by Skylar Tibbetts, which grew out of a programmable matter project in my lab. This is Formlabs, which is a 3D printer company that grew out of students in my lab. In the short term, we work on that. But if you take the Formlabs Form 1, which is one of the highest resolution consumer 3D printers, take the Form 1. There's a very small set of things you make. You can't make functional electronics on it. when you build on it, if you don't get good adhesion to the build plate, it peels off and the print is failed. If the resin is old, it doesn't cure properly and the print fails. They have a few types of materials, but you can't make arbitrary mixed materials through the same process. And when you're done with your print, you might be able to grind it up and make something out of it, but there isn't much you can do with it. It's fused resin. The research we're doing upstream on this is designing an assembler that assembles assemblers. It makes complex computing, communicating, electromechanical system by placing little volume elements of high performance semiconductors, conductors, insulators, magnetic materials. So in one process, you can make a complex multifunctional system. When you build, you can locally detect and correct errors. So mistakes don't accrete, and you can keep building, and there isn't a limit to the build size. And to the last question, it's disassemblable. So the difference is the material is in a continuum. The material is discretely assembled. And the difference between 3D printing as fusing and assembling is as simple and as profound as the 10-year battle at the phone lab between a phone call as a waveform and the phone call as a symbol. It's putting a code into the construction so you can detect and correct errors.
Okay, thank you.
Yep.
Thank you for being here. It's an honor to be able to ask you a question.
Thank you.
I have a concern of the growing gap between our wealthy and our poor. And I'm just wondering, with your fabulous Fab Labs, what kind of an effect it will have in terms of offering opportunity to maybe, for instance, somebody currently sitting on welfare to be able to study, to learn, and participate in what may not be about economics or incomes, but whatever the current future brings.
Yeah, so what's interesting about that, again, it's not utopia, but what's interesting about it is mobile money came to Kenya before Durham. Most of you don't use your phone to pay things. It's long since happened in Kenya, for example. So we're catching up to them. In the same sense, let's see, Ugyen right now is doing the Fab Academy in Pabal. Pabal is one of the poorest, driest, most remote parts of India. It has a wonderful Fab Lab that has interesting story for why it's there. For sort of ever, people have moved into cities in India for opportunity. And there's a lot of attention to urbanization and smart cities. But cities in India are crowded, they're polluted, you don't get much space. Something really interesting happening is ruralization rather than urbanization. People are so this Fab Lab in Pabal, it's a little tiny town. They have a full Fab Lab, but they have good internet, and they're part of the global video meetings and part of all kinds of collaborations. And I spend time with them each week through the network. But when you go to Pabal, there's actually fresh air. And there's space, and there's trees, plus you get a Fab Lab, plus you get good internet. And so people are actually leaving the cities to go to a little village like Pabal because life is actually better there. And so, if you look, this is called Insight Focus, Blair's lab in Detroit. Jonathan Ward, who's a student of mine at MIT, who worked with Ted, who worked in Silicon Valley. He's now based with Blair in Detroit, not to do outreach, it's because he's happiest there. He feels best in the community there. He still does some work, I think he's still working with you. He still does some work with Ted, but he's based with Blair in Detroit, not for a social mission, but because it's the most, it's moving towards this new sense of economy, and he's happiest and most productive there. And so if you take the Barcelona example, there's all this coverage of Catalan separatism versus nationalism. But when nobody's looking over of Detroit, you haven't heard about Blair. Sort of in each of these stories, a new kind of model of an economy is trickling up, but it's not where the press is looking. And it's not based on the traditional axis of haves and haves not. And so it's kind of an end run around that bottle, and it's already happening, but it's just not where people are looking.
If you can take one brief question. Is there a fusion?
Let's make this the last question.
Okay, I was wondering about energetic constraints on how many people can do and how easily, whether the same materials are used, if there's a common denominator that concentrates what materials used, and perhaps, is there a way of extracting energy fusion research?
Let me talk more broadly about energy. One interesting set of projects in Fab Labs is local energy conversion. And if you look at the net influx of the big fusion reactor in the sky of solar power and wind power, we have plenty of energy flux on Earth, but the issue is the difficulty of converting it and getting it to where you want. And so there's lots of interesting work on Fab Labs on doing not megawatt or gigawatt turbines in the middle of the desert, but local energy conversion. But the more interesting thing lurking behind that is in this Fab City project, cities are committing to produce what they consume in this 40-year countdown. But interestingly, to do that, you need to know what you consume. And so if you were to go to Durham and ask Durham City Council, what are all the fluxes into and out of the city? Turns out nobody knows, nobody measures.